Hello friends, welcome to my YouTube channel. In this session, we'll see about the Coulombs law in detail. So what is an electrostatic field? So electrostatic field is produced by the static charge distribution. It is a time invariant function. So the applications of electrostatics are electric power transmission, X-ray machines, lightning protection, photocopiers, liquid crystal displays, spray painting and many more. There are two fundamental laws under the electrostatic fields. One is Coulomb's law, the other one is the Gauss law. So we'll see what is Coulomb's law first. So it deals with the force a point charge exerts on another point charge. So two polarity charges may be positive or negative. We all know that like charges repel each other and unlike charges attract each other. If both the charges are positive or if both the charges are negative, like it means like charges. So like charges will repel each other and whereas unlike charges will attract each other. So the charge is measured in coulombs. So 1 coulomb is approximately equivalent to 6 into 10 to the power of 18 electrons. So 1 coulomb is and 1 electron is 1.602 into 10 to the power of minus 19 coulomb. So a proton has a charge of E and an electron has a charge of minus E. So atom that has lost one or more electrons gives a net positive charge. If it gains one or more electrons, it gives a net negative charge. Now we'll see in detail what is Coulomb's law. So Coulomb's law states that the force F between the 2 point charges Q1 and Q2 is along the line joining them and is directly proportional to the product of two charges Q1 and Q2 and is inversely proportional to the square of the distance r between them. Let's say the expression of Coulomb's law. So the force F between the 2 point charges Q1 and Q2 is along the line joining them and it is directly proportional to the charges q1 and q2 and inversely proportional to the square of the distance between them. So and it is multiplied by a constant term k. So this constant term is nothing but 1 by 4 pi epsilon naught. So we can replace k by 1 by 4 pi epsilon naught. Therefore, F is equal to Q1 Q2 divided by 4 pi epsilon naught into R square, where epsilon naught is the permittivity of free space and the value is a constant value. It is nothing but 8.854 into 10 to the power of minus 12, or we can also use 10 to the power of minus 9 divided by 36 pi f by m. So where k is a constant, k is nothing but 1 by 4 pi epsilon naught. Now, what is Coulomb's law? Let's first see what is this diagram explanation. So the figure illustrates the interaction between the 2 point charges using the Coulomb's law. So there are 2 point charges Q1 and Q2 and the origin is taken as the reference point. So I'll repeat again, there are 2 point charges Q1 and Q2 and the origin is taken as the reference point. Now R1 is the position vector of charge Q1 from the origin and similarly R2 is the position vector of charge Q2 from the origin. R12 is nothing but the displacement vector or the distance vector between the charges Q1 and Q2. So mathematically the force F is equal to K Q1 by Q1 Q2 divided by R square. So by replacing K we will get Q1 Q2 divided by 4 pi epsilon naught R square. So we need to find the force F12 on Q2 due to Q1 is given by F12 is equal to Q1 Q2 divided by 4 pi epsilon naught R square into A vector, where your distance measure is R12. So this vector can be represented as R2 minus R1 divided by magnitude of R2 minus R1 the whole square. So since Q1 Q2 as it is remains the same, 4 pi epsilon naught ordinary remains the same and the unit vector is nothing but vector divided by its magnitude. So R2 minus R1 divided by R2 magnitude of R2 minus R1, that is your A. So already one R square is there, and therefore F12 is Q1 Q2 into R2 minus R1 divided by 4 pi epsilon naught magnitude of R2 minus R1 the whole cube, where the unit vector is nothing but R12 divided by R. R12 is nothing but R2 minus R1, and therefore we can write R is equal to magnitude of R12. Okay. Now F12 is equal to Q1 Q2 R2 minus R1 divided by 4 pi epsilon naught R2 minus R magnitude of R2 minus R1 the whole square. So similarly, we can also write the force F21 on Q1 due to Q2 can be written as F21 is equal to F12 into the unit vector. So it is nothing but F12 minus of the unit vector, or we can write the force F21 will be opposite in direction of F12. So the distance r must be much greater than the dimensions of charged bodies Q1 and Q2. So you have to maintain the distance in such a way that it must be much greater than the dimensions of the charged bodies Q1 and Q2. And Q1 and Q2 is assumed to be static, and signs of Q1 and Q2 should also be taken into account. Suppose if there are n data point charges Q1, Q2 up to Qn located at points with position vectors R1, R2, so on up to Rn, the resultant force on a charge Q located at a point with position vector R is given by using the principle of superposition. Therefore, F12 is equal to Q1 R minus R1 divided by 4 pi epsilon naught magnitude of R minus R1 the whole cube plus Q2 R minus R2 divided by 4 pi epsilon naught magnitude of R minus R2 the whole cube, and so on till Qn R minus Rn divided by 4 pi epsilon naught magnitude of R minus Rn the whole cube. Therefore, we can write in a simplified form as F12 is equal to Q by 4 pi epsilon naught summation of K is equal to 1 to N Qk R minus Rk divided by magnitude of R minus Rk the whole cube. So this is the version of the above equation. Now, we have to see what are the electric fields due to the continuous charge distribution. So this is how a point charges look. So there are three types of continuous charge distribution. One is the line charge, where the charge is distributed uniformly along the line. Similarly, the next one is the surface charge, where the charges are distributed uniformly around the surface charge. And then the volume charge, where the charges are distributed in a volume. So these are the three types of charges under the continuous charge distributions. Now, electric field due to continuous charge distribution, and for line charge density, the charge density is represented by rho and line charge density is represented by rho L, and it is expressed in Coulomb per meter. Similarly, the surface charge density is represented as rho. Surface charge density is represented by a suffix S. So it is rho S, and it is measured in coulombs per meter square. Similarly, the volume charge density is represented as rho v, and it is measured in coulomb per meter cube. So to find the charge element dq, so we need to find dq is equal to rho L into dl is nothing but q is equal to, so the charge dq, the differential charge is equal to rho L into dl for a line charge. So if you want to remove this differentiation, we need to put an integration in the right hand side. Therefore, Q is equal to integral L rho L into dl. So this is for the line charge. Similarly, we can also write the charge element dq for surface charge and the volume charge. For surface charge, dq is equal to differential charge is equal to rho s into ds, and therefore if you want to remove this differentiation, you need to introduce an integration in the right hand side. Therefore, q is equal to integral s rho s into ds. This is for the surface charge. Similarly, for volume charge, dq is equal to rho v dv, which tends to q is equal to integral v rho v into dv. The next is E of a point charge. For a point charge, how the electric field is represented. So E is equal to Q divided by 4 pi epsilon naught R square into the unit vector. This is the reference equation. Now you can replace the Q by a line charge, by a surface charge, or by a volume charge. So by replacing Q by charge elements and you are integrating it, we can get E is equal to integral L, because previous slide we have seen the charge Q is equal to integral rho L dl. So replacing the Q with those line charge, surface charge and volume charge, we can write E is equal to integral L rho L dl divided by 4 pi epsilon naught R square into the unit vector. The unit vector can be written as R vector divided by magnitude of R vector. Similarly, for the surface charge, E can be written as surface integral of rho s ds divided by 4 pi epsilon naught R square into the unit vector. Similarly, for the volume charge, E is equal to integral V rho v dv divided by 4 pi epsilon naught R square into the unit vector. Now let's see for the line charge how we can find the electric field. So the first one is field of a line charge. So you consider a uniformly charged line of length L. So I have represented over here. So we are going to consider a uniformly charged line of length L. The whole length of the wire is L, whose linear charge density is represented as rho L in Coulomb per meter, because we are seeing for the line charge the unit is Coulomb per meter. Now in this uniformly charged line of length L, you just consider a small length, small element dl at a distance L from one end of the charged line. So we are going to consider a small distance dl. So this is dl. So its length from the dl to this point will be small l. Now let P be a point at a distance x from the element dl. So we are just joining the line over here. Let P be at some space, and let P be a point at a distance x from the element dl. Therefore, we want to find what is the electric field at the point P. Now extend this line, so this will become the D with respect to the electric field x direction, and this will become with respect to the y direction, electric field with the y direction. So we need to find at the point P what is our electric field. So the electric field at the point P due to the charge element rho L into dl is given by dE is equal to this line. dE is equal to, for a line charge, it is given as rho L dl divided by 4 pi epsilon into R square. The basic formula which we have seen before, the same I have represented over here. There in the previous slide it was 4 pi epsilon naught, where in free space it is epsilon r is equal to relative permittivity is equal to 1. So we have replaced epsilon by epsilon naught. Here just I have put epsilon. So epsilon is equal to epsilon naught into epsilon naught. So your D, the electric field at the point P, is given as rho L dl divided by 4 pi epsilon into R square. Now let us take the that small triangle alone. So this where the theta comes, where the DE parameter, that the triangle we are going to take. So we are going to find the xy components of the electric field with respect to the DE line are given by DEX is equal to DE sin theta. So DE sin theta, in sense it is similarly DEY can be written as DE cos theta. So therefore the equation 2 can be written as dEx is equal to, instead of dE, in the earlier slide we have seen dE is equal to rho L dl divided by 4 pi epsilon R square. Just replacing this dE with that equation, equation 1, we can write dEx is equal to rho L dl divided by 4 pi epsilon R square into the sin theta as it has come. Now from this triangle we are going to find what is cot theta. So cot theta is nothing but adjacent divided by opposite side. So as per this triangle, the adjacent is x minus L and the opposite is h, right? So just rearranging this equation, we get x minus L is equal to h into cot theta. Now differentiate with respect to L. So when you are differentiating with respect to L, minus of dl is equal to, and differentiating with respect to L and theta, so we'll get minus dl is equal to h into differentiation of cot theta is nothing but cosecant square theta into d theta. Now both the signs minus sign is there, so we can write dl is equal to h cosecant square theta into d theta. Similarly, for this triangle, if we find what is sine theta is nothing but opposite side divided by hypotenuse. So sine theta is h by r. Just rearranging, we get r is equal to h by sine theta. So 1 by sine theta is nothing but cosecant theta. Therefore, r we can write it as h cosecant theta. Now substitute this equation 5 and 6 in equation 4. So we know what is dl, what is r term. So we just try to substitute the equation 5 and 6 and 4 in 4. So we can write dx is equal to rho l, instead of dl you replace with h cosecant square theta d theta, and the sine theta as it is will come, and then divided by 4 pi epsilon r square. Instead of r square we'll replace with h cosecant h square cosecant square theta. So as it is we have written. Okay, so instead of dl we have replaced h cosecant square theta d theta. Rho l retains the same, and sine theta as it has come, and 4 pi epsilon as it is we have written, and only for r we have replaced with s square cosecant square theta. Now we can write it as rho l sine theta h cosecant square theta d theta divided by 4 pi epsilon naught h square cosecant square theta. Now you cancel out all the possible terms, and the final result will be dx is equal to rho l sine theta divided by 4 pi epsilon h. So the electric field Ex due to the entire length of line change is given by, now this is in terms of differentiation. Now we need to solve and find what is the electric field at the direction of x. So we can write Ex is equal to integral alpha 1 to pi minus alpha 2, and then rho l sine theta divided by 4 pi epsilon h into d theta. Now first you integrate it. So integration of sine theta, the rest of the terms rho l divided by 4 pi epsilon h is treated as a constant, and integration is with respect to sine theta. So integration of sine theta is nothing but minus cos theta, and you substitute the limits alpha 1 to pi minus alpha 2. When you substitute, you will be getting Ex is equal to rho l divided by 4 pi epsilon h cos alpha 1 plus cos alpha 2. Similarly, we can also find for y component what is the electric field. So Dy is equal to rho l dl cos theta divided by 4 pi epsilon r square. So we have found Dy is equal to dE into cos theta. So dE into cos theta, dE is nothing but rho l dl divided by 4 pi epsilon naught r square. So we get Dy is equal to rho l dl cos theta divided by 4 pi epsilon r square. Now as usual, the same procedure what you have followed over there for dEx, you repeat the same and substitute the 5 and 6 in equation 9, and therefore in the place of dl you will be substituting uh, the cos theta term and cosecant square theta term, and for the r square you will be substituting h cosecant square theta. So on substituting you will get rho l cos theta d theta divided by 4 pi epsilon h. Cancelling out the possible terms, we will be getting rho l cos theta d theta divided by 4 pi epsilon h. Now you have to cancel this differentiation. You want to have what is the electric field in the direction of y. Therefore, this differentiation will become integration in the right hand side. So Ey is equal to integration of alpha 1 pi minus alpha 2 rho l cos theta d theta divided by 4 pi epsilon h. Now the rho l divided by 4 pi epsilon h is treated as constant. So the integrator term only will be the cos theta d theta. So integration of cos theta is nothing but sine theta. Now you apply the limits, and therefore you will be getting Ey is equal to rho l divided by 4 pi epsilon h into sine alpha 2 minus sine alpha 1. So we got the 2 points Ex and Ey. So Ex is nothing but rho l divided by 4 pi epsilon h cos alpha 1 plus cos alpha 2. Ey is rho l divided by 4 pi epsilon h sin alpha 2 minus sin alpha 1. Now we have two cases. Suppose if the point P is at the bisector of the line, then alpha 1 will be equal to alpha 2 will be equal to alpha. Therefore, your Ex term will become, instead of alpha 1 alpha 2, you just replace by alpha. Therefore, you will be getting Es is equal to rho L divided by 4 pi epsilon h cos alpha plus cos alpha. So, you will be getting 2 cos alpha. So when you add, you will be getting 2 cos alpha. This 2 and this 4 will get cancelled, and therefore you will be getting E electric field in the direction of x will be rho L divided by 2 pi epsilon h into cos alpha. The next case is you are considering the line is infinitely long. So far we have considered only a finite length of wire. Now the second case is if the line is infinitely long, then your alpha will be equal to 0. And therefore substituting this in your Ex term, you will be getting cos 0 plus cos 0, and therefore cos 0 is nothing but 1. Therefore 1 plus 1 you will be getting 2, and this 2 and this 4 will get cancelled, and therefore you will be getting E is equal to rho L divided by 2 pi epsilon h. Similarly, we need to find Ey. So what was the equation for Ey? Ey is rho L 4 pi epsilon h into sine alpha 1 sine alpha 2 minus sine alpha 2. So when you substitute sine 0, you will be getting sine 0 is equal to 0. Therefore, your entire Ey term will become 0 for the case 1 as well as for the case 2. Thank you. Let's see in the next session.